Great.
But yes.
Bye.
Hey, Dorit. Okay. Wait.
Set up? Start?
Well,
Yeah.
so.
Wait, don't rotate it this way. I will.
למה? רגע, בוא נשים את זה פה על כיסא. שנראו בערך מה קורה אוקיי, בסדר.
Now you can see the crowd.
Sharing is not turned on, by the way. Yes, I can see the crowd.
פתח אופציה לשיר, אני לא הוסט.
איתי, אתה יכול לעשות אופציה לשיר? אתה יכול לעשות אותנו הוסט?
So presumably I'm supposed to share my screen. Yeah.
No, we can hear you.
Yeah. You cannot hear me?
Yeah, we hear you very well. We are working
Okay.
now.
All right.
רגע,
You want to try to share?
Okay. רגע, one second. One second.
This actually looks promising.
Yes. Okay, true. Yeah.
Show my intro slide.
But can
you see this?
Yes, we can.
Very good.
Okay, great. So we're happy to host in our gathering Benedict, and also later Vedika will join the discussion. And I'm very glad that, so what you see here, Benedict and Vedika, are the survivors of the fourth full day of talking about local disability and error correction and self-correction. And so we're very much anticipating what you have to say about how everything here is connected. So without further ado, we will ask, so the habit here is to ask a lot of questions. So I hope you will hear us and
okay.
how it will work out. I don't know, we'll see.
Okay, yeah, we can see. So I should expect questions in between? I will see when I hear someone.
Yes. Maybe I will sort of tell you like that there are questions.
Yeah, okay.
Okay, great.
Very good. All right.
Yeah, and Dorit, since this is kind of the end of your day, if you want to steer the conversation towards some topic that you were hoping Benedict covers and we're not, then just interrupt and we can just like have it relaxed and have fun. Yeah.
Okay, Benedict, floor is yours.
Thanks, Dorit, for the nice introduction. As Vedika said, we can be relaxed and have fun. But okay, I prepared to talk about topological cognitive spin glasses in qLDPC codes, which is what we've been doing now for a while. And of course, first I should acknowledge the collaboration. Of course, Vedika, who's here, who was a senior author in all this, and then Tibor, who did a lot of important work in getting this together, and also Nico, who is our, I guess, in-house expert on codes actually, and then Grace, who did some very nice calculations also for the classical spin glass part. Okay, and without further ado, let me start. And just to start super high level, of course, we are somewhere situated here between many-body physics on the one hand and information theory and computation theory on the other hand. And well, at least on the left side in physics, the slogan is, of course, more is different by Anderson. And what does it mean is that condensed matter physics in many cases is the study of emergent properties. So the question is, in what cases do collections of interacting particles behave differently from their constituents? Right? For example, the fractional quantum Hall effect, you get fractional charge carriers even though the system is made up of electrons.
Benedict, I want to stop you just a moment just to let you know, to remind you that a third of the crowd is physicists, and a third is mathematicians, and a third is computer scientists. So just to let you know that everything you say, about 2/3 of the people don't understand.
Yeah, I mean, please ask. I hope this is I hope this is still high level enough. But okay, so physics and traditionally physics is really about kind of the study of universal phases of matter in materials in nature, right? So this is what physics or condensed matter physics is about. And this, of course, sounds very different from what computer scientists do. But I guess I'm trying to convey here that maybe there's some similarities even conceptually, in the sense that, okay, I didn't find a similarly catchy slogan for computer science, but I looked at Shannon's biography, and there at least they say why kind of his work was so foundational. And that is, of course, because in some sense he showed that noise doesn't have to be accepted as a fact of nature, but you can fight it. And of course, you do fight it by using kind of more of the same thing. That is, you encode information redundantly, and you get something out that is not noisy. So it's different in some way. And more generally, computer science is interested in scaling, right? For example, Shannon asked about the capacity of a channel in the presence of noise. Complexity theory asks about how much more difficult problems get as you increase their size. And these are not so unrelated maybe to the idea of kind of emergent properties. How do many things behave together? And okay, this is maybe a conceptual point, but there are examples, maybe some of which you have seen today or in the other days, where these really coalesce, both fields. And one example, for example, is of course decoding of the toric code. For example, so I'm not sure the toric code has been introduced, but okay, if you don't know what it is, it's a very...
It was introduced.
Very good. It is a very useful code that is also implemented in an experiment. And as a function of noise strength, right, the toric code undergoes a transition from being decodable to not being decodable. So you can use it or you cannot. And this transition can be directly related, with a certain model for the noise at least, to a ordering transition in a dirty ferromagnet, which is the random Easing model. So there's a direct relation between kind of the transition in the phase of matter and kind of a transition in a computer science context. And another example, for example, maybe that's more related to complexity theory, it is the idea of algorithmic hardness transitions, where kind of as a function of kind of which problem you consider, say clause density in a constraint satisfaction problem, the problem gets more or less hard to solve as a function of size. And this has been related, for example, actually to the physics of spin glasses in physics. And so we are slowly maybe closing in onto the topic of that I want to talk to you today. All right. Then, okay, somewhat more concretely, the setting we are today, and I guess what the day today was about, is the fact that actually, I guess, the connection between many-body physics and information is very evident in the fact that we can encode information robustly and redundantly in degenerate and macroscopically distinct states of many-body ordered phases. And of course, the poster example of this is a classical magnetic hard drive, right? So a magnet is something called symmetry breaking order. You break the time reversal symmetry or the kind of bit flip symmetry of your magnet. And this is what's used in a magnetic hard drive to encode like a sequence of bits, right? And either you are positively or negatively magnetized. In the quantum setting, this is of course a bit more complicated, but it's still a form of order that in physics is called a topological order, because it cannot be locally distinguished from each other. And it's a highly entangled state of matter in this case as well. And of course, in the absence of good materials, what people do is they build kind of these states artificially in the lab. And for example, Google, for example, Santa Barbara has at least, and of course, by now at this point, many others have, I guess, given good experimental evidence that at least some form of topological ordered states on small scales has been realized in the lab. Although in this case, in a very artificial setting, maybe. And just to foreshadow what's to come, one obvious question, of course, in this context, are ordered states really all there is to it? Right? Is ordered states the only things that you can use to encode information? Or is there other settings? And well, the answer, of course, will be yes, there is. Hopefully, I'll get to that.
What do you mean by ordered states exactly?
I get to that in a bit, actually more in detail. I mean, on some level, it's symmetry breaking what I mean. So are the states that you use to encode information related by a symmetry? I'm not sure this helps. Does it help?
Yes, a bit.
That will be what I mean. So spontaneous symmetry breaking is for me order. I guess I'm a physicist. All right.
For now, it helps.
Okay, I'll get to this in a bit more detail in a second. But before I go actually to that point in more detail, let me just quickly say one second what I will not discuss. And one thing that I will not discuss today is active error correction. Because of course there's kind of two ways. You will probably have heard also about active correction, where kind of the idea of the whole procedure is that you have a system and you measure some properties of the system. You use these measurement outcomes to do some classical processing and then some active feedback. So this is this loop sketched here. Right? And what you should think about here is that you're kind of trying to push the system into a zero temperature state, for example. And because your lab is at a finite temperature, so you have to kind of keep the system actively out of equilibrium via this measurement and feedback loop. And okay, so this is, for example, what a lot of these experiments do. But of course, what would be nice to have is a passive memory. And in a passive setting, this idea is a bit different, which is that you take a state and you encode it into some macroscopically degenerate state, for example, a ferromagnet, right? And then you just can wait, and you put your system in the fridge and you wait. And even after a long time, you can come back to the system and decode. So you can infer what you originally encoded into the system from its state at a much later time. So there's an active step at the beginning and the end, but in between you have to do no work, except for cooling. And this will be the system that we look at today. So this is self-correction. So I guess this is how you have been looked at in detail. And this happens at positive temperature. And okay, so just give a few examples from a physics perspective. I looked at the schedule a bit, and I guess you have discussed actually both of those. And of course, the simplest example, I guess, is a two-dimensional Ising model in the ferromagnetic phase. So we are at low temperatures. And at low temperatures, there's two distinct stable states, which are macroscopically different. They have a positive and a negative magnetization. In physics, what we often do to also illustrate is we draw these cartoons of a free energy landscapes with like two distinct minima, right? And both states correspond to kind of living in one of these two global minima. And if you look at them in the lab, right, they would look something like this, where they are either majority down or majority up, the spins. And this can encode a 0 or a 1. And then in the quantum setting, you have to do a bit more work. In particular, you can't do it in low dimensions. You have to go to 4D. But then the 4D toric code, for example, that is a self-correcting memory. I guess this was an explicit point in the schedule today. So I won't explain this too much. But what is important is in both cases, actually, the states that you use to encode the memory are symmetry related. So if you're a computer scientist, the operational thing you can think about is the logical operator of your code preserves the energy of the system. This is true in both the Ising model and the 4D toric code. In the 4D toric code, of course, it looks a bit more complicated, the symmetry operation. It's some sheet of spins. It's a higher form symmetry, we would say in physics, but it's nevertheless a symmetry. And okay, so I left the second half of the page blank for now. And well, what I want to say is there's more than order. And classically, this is well appreciated. And it comes in the form of spin glasses. And if you're a physicist, you would call these things maybe p-spin models or diluted p-spin models. If you are a computer scientist, you would call them Gallagher codes. So random LDPC codes. And in these settings, if you draw a similar cartoon of a landscape, you would see something like this. Okay, this is how it cartoon. But the point I want to get across here is that you will have stable minima, which are also dynamically stable, so you can use them to encode information in a passive way. But they actually live at different energies. So they cannot be related by an operation that preserves the energy of a system. So in this case, you have basically memory without order. Right? So this would be the catchphrase of physicists say. You could think of memory that is beyond just symmetry breaking. And well, of course, the point of this talk is kind of to fill out this bottom right corner here, which is now the question: can we also get kind of quantum memory in a setting where we are beyond just a spontaneous symmetry breaking of like some higher form symmetry, as in the Topological code. And okay. Yeah, this is indeed, I guess, the main result of our question. I see Dorit trying to grab the mic.
Yeah, I'm kind of hesitating about the question. By the way, everyone, I'm not the only one who probably wants to ask a question. So my question is, are there no cases where the energies are the same? Benedict, you see me?
Yeah.
Here you are.
No, when you speak, do it when you
Yeah,
speak.
I understand. When I speak, I see myself. My question is, what if, could you have lack of order but still same energies for all the states that you're interested in? I mean, is the issue really the energy?
No, I mean, I guess it's a one-way
energies are-
implication. If you don't preserve the energy, you can't be a symmetry.
Yeah, I understand. But if you do preserve the energy, is it always symmetry break? Is it always just symmetry breaking? Is this?
Well, if you preserve the energy, I guess, for all states, I would call it a symmetry, because then you are like kind of some operator commutes with the Hamiltonian, right? So this would be one operational definition of a symmetry. But of course, you can have something like, say, a T-gate in the color code or so, right? Which preserves the kind of energy of the ground state, but not of all states. So that would be maybe what we would call an emergent symmetry in physics.
Okay.
Is this helping?
But I think if you have a degenerate ground state subspace that is robust in some way, I don't know of a way to get that without symmetry, either higher form symmetry in topological order or conventional zero form symmetry and symmetry breaking. Higher form symmetries are absolutely stable, so the ground state degeneracy is robust to any perturbation. Whereas if you have conventional symmetry breaking, then you need to add perturbations that respect the symmetry. But I think it's the stability that's the question. There's always fine-tuned ways to get some degenerate subspace, but if it's going to be stable, then I think then I don't know how to do it in a way that's stable, which is not coming from some kind of symmetry.
Ellie, did you want to ask something?
Yes, I wanted to ask.
Let me
Yeah.
just open the mic.
So I wanted to ask if you care about color code for what you are doing, because you mentioned something about color code. Is it really important?
Oh no, I was just trying to give an example of an emergent symmetry, like where you only kind of preserve kind of the ground state subspace, but not all states. Sorry, maybe that was more confusing than helpful.
But yeah, I think the general philosophy is that on the things that are in the left column of Benedict's slide, you have some degenerate ground state subspace protected by a gap. And if you add perturbations, when you're doing the symmetry breaking order, then your perturbations should respect the symmetry. The gap will remain open, your ground state degeneracy remains protected, and your code is stable to symmetric noise. So for instance, bit flip noise for a classical repetition-like code. And then when we have topological order, again, we have a gap of ground state degeneracy, absolute stability, and then the code in turn should be stable to all types of local uncorrelated errors.
Sorry, so you're saying so on the left you would be stable to all types of errors, including the depolarizing noise, for example? That's what you're saying?
Well,
For topological order, right?
Mm-hmm.
But for symmetry breaking order, like an Ising magnet is not stable to the addition of a longitudinal field. And in the classical code, there is no notion of protection against dephasing in that case. But it is stable to the addition of an X transverse field. And likewise, it's stable to bit flip errors.
Okay. So I think we can continue, right? Yeah. Benedict?
shall I continue?
Yes. Let's.
Okay. Sorry. All right. Okay. So with that kind of build up, let me give a high level overview of what we actually found and what we showed. And of course, I guess the big headline result is that we have a new phase of matter, which we call a topological quantum spin glass, and which kind of combined features of glasses and of topological order. And this is an example of a system with long-range entanglement and quantum memory at finite temperature, but having these properties not only in kind of a ground state, but also in kind of highly excited states at finite energy density even. So in that sense, it's different from the toric code. And okay, so a new phase of matter, of course, as a physicist, is always an exciting thing. But I think even as a computer scientist, I think there's some interesting things to be learned here. One thing is, okay, there is self-correction here, so quantum self-correction, but it's really quite a different mechanism from that of the 4D toric code. And it happens in a setting where the system is really in a phase that is just beyond just standard symmetry breaking or standard topological order. And maybe more operationally, from a code perspective, right? This is really the phase in this way that you should think about when you think of good qLDPC codes. And what is nice, what we find actually, is that they generically actually encode many copies of themselves in their excited states. So I will say a bit more about this later, what this means on a technical level. But kind of, you cannot only use the ground state, you can also use these excited states. So there's many copies of the same memory embedded into the landscape. So this is kind of an operational thing. And then something that's, I guess, not formally the topic of this talk, but I also find kind of nice, is that actually our techniques that we developed in solving these questions actually gives a new perspective also on some classical glass problems. And we were able to get some new rigorous results on kind of finite connectivity spin glasses. So these are models that are interesting in kind of theoretical physics and in certain areas of kind of probability theory. And to the best of knowledge person, we get the first rigorous proof of finite connectivity spin glass order.
So, Benedict, is it true that the second rectangle, basically, can I interpret that as you showing that, first of all, we've discussed today at length the quantum LDPC codes. You showed that those are self-correcting, right? Quantum self-correcting.
Well, this was actually, so I should be clear. So the fact that they were self-correcting from the ground states, that had been shown before us. So there's a paper by Yifang Hong and Andrew Lucas on self-correction from the ground states. And we generalized kind of this statement to these local minima.
But in any
and the fact that you can start in kind of, that there's much more going on than just ground state order.
Well, and I think even before Andy's paper, right? Like the original papers themselves came with a local decoder, which was just
That's true. Yeah.
Which
And the fact that it was-
basically,
yeah, exactly.
which to a physicist is just zero temperature Monte Carlo. So I think, I think for us, I think the main contribution was like other types of codes we tend to think of as some kind of phase of matter, right? Like classical codes, like the repetition code to a physicist is a Ising magnet. The toric code to a physicist is a Z2 gauge theory with topological order. So now we have all of these great codes, and what are they physically, right? Like what kind of phase of matter do they correspond to? So I think that's maybe some of the second bullet.
Yeah.
So are you claiming that any NDPC code that has a local decoder is basically a self-correcting code?
I think so. No, well, no, because you can have a local decoder that breaks detailed balance, right?
It depends a bit how the local decoder looks like, I would say. For example, in this case, the flip decoder looks very, very much like global dynamics, right? If you look at Silver's Spearman. So then, as a physicist, you really read this and think like, okay, this ought to be stable under global dynamics.
Okay, good.
So it's more than just having a local decoder. It's also that local decoder looks very, very much like what you would naturally write down as a model for self-correction.
Okay, so I have a few more questions, but let's continue after that.
All right. So the final thing that I want to advertise is, and I will get there, is a fundamental technical result. So maybe that's also not, again, in the interest of this talk. But on the way, we kind of proved basically fundamental theorem about the theory of quantum channels, I would say, which is a bottleneck theorem for quantum channels. And if you're familiar with bottleneck theorems from the classical context for Markov chains, this is a straightforward generalization of that result from the theory of Markov chains to quantum channels. And in this case, we used it to get kind of to a dynamical view of quantum phases. And you also use it to prove the self-correction. That's on a technical level, you have to use it. But then also, for example, it can be independently of this, it can also be used to bound, for example, the performance of certain dissipative quantum algorithms. So it's, I think, interesting independently of our results. All right, so these are the results that I will, well, hopefully make plausible in the remainder of this hour. All right. And with that, let me set the context more concretely. So this project started by kind of an endeavor, I guess, of all four of us, Theo, Vedika, and Asnika and me, to understand a bit good low-density parity check codes from a physics perspective. Because as Vedika said, right, we have all these nice toric codes are kind of nice for physicists as well, and we have all these views of many codes as interesting phases of matter, and then of course these good qLDPC codes came along. And the obvious question is, okay, how do we think about them? And just to kind of remind you, LDPC here means graph locality. So if you're a computer scientist, think of checks, right? So you have a parity check code. Every check involves finally many qubits or bits, and each qubit is also part of finally many checks. So if you're a physicist, your model is graph local and has an extensive energy. If you're a computer scientist, this means kind of that the tenor graph has finite degree, for example. And in general, of course, codes are, I mean, beyond LDPC, codes are usually like kind of summarized in three distinct integers, that is NKD. N is the number of physical qubits, K is the number of logical qubits, how much information can you actually store, and then there's the code distance D, which tells you how robust are you. And we call a code good if both K and D scale with N. So good is here a technical term. So this is basically the lowest possible overhead, at least in a scaling sense, and the strongest robustness that you could expect, and both at the same time. And it's very amazing that this is possible, but it definitely requires something called expander graphs. So Brabi, Puller, and Tehal in 2010 already showed that kind of it's not possible to get a code like that is local in any finite Euclidean dimension. So you need something like an expander graphs, and classically, actually, the graphs that you use to define the models, you can still kind of draw nicely in 2D. Could be a hyperbolic space, like something like this. This is a regular tessellation of hyperbolic space, or it could be something like a regular graph, which actually locally looks a bit like a tree, and then you connect up kind of the leaves in some random way, for example. This would be an example, just operationally. But in general, the definition is that, okay, if you take some subset of vertices S, and for example, that's less than half your system, then the number of neighbors of S, so the number of edges that leaves S, is proportional to the size of S. And so this means, maybe colloquially said as a physicist, you would say the boundary of any subregion scales with the volume of the subregion. So this is, of course, not possible in Euclidean. And of course, the big breakthrough recently was that they were quantum. So classically, kind of there's constructions by Gallagher and Sisler Spielman, which use these kind of graphs to construct good asymptotically good codes. And then the recent breakthrough is that this has been generalized to quantum. And okay, so maybe now, if you are a physicist that is more experimentally inclined, you tell me, oh, but an expander graph that looks kind of unnatural. But one thing I think that I do want to say is that now is a better time to study these kind of geometries than ever, because we have a lot of emerging experimental problems which actually can implement non-local connectivity. Of course, there's these amazing videos by Michel Lukin, where the atoms are dancing and you can implement kind of basically arbitrary connectivities. But even in a more conventional superconducting qubit setting, people have implemented finite patches of a hyperbolic space. And then there are these experiments by the group of Monica Slyer-Smith in Stanford, which kind of put atoms in a cavity to at least within the cavity locally some long-range connectivity. So there are these new experiments with an incredible level of control. And in some sense, this just naturally kind of broadens the frontier of what you should be interested in as a many-body physicist, I think. All right, this is just to say it. Good. So this is the last setup slide. So now let me actually introduce maybe one concrete example of a model we would look at. And okay, so how do we actually build a quantum LDPC code? And maybe what we start from usually is we start from a classical LDPC code, and then we do products. So classical LDPC code, if you know what a Gallagher code is, that's what it is. That's what I'm going to talk about. If you know what if you're a physicist and you know what a diluted p-spin glass is, that's what I'm going to talk about. Otherwise, I'm going to tell you what we are doing is we write down a Hamiltonian. And what we will do to write down the Hamiltonian is we will define a number of bits or
Let
Ising.
me just stop for a second. I'm not sure that it was said that what Amnon described this morning was Gallagher codes. Was it said?
Sorry? You
No,
have done Gallagher codes?
I'm just talking to people here and asking if, so Amnon described this morning random LDPC codes, and I just wasn't sure that he did actually describe Gallagher code. He describes Simpson-Spillman code. Okay, but we could think of them as basically the same, no? Nati, this is a question for you.
Close cousins.
Close cousins. Okay.
Yeah, I mean, Simpson-Spillman, you would take a graph decorated, right? And here you just choose a random kind of bi-regular graph as the Tanner graph, yeah.
Okay. So don't assume, we know at this point of the day, we basically hardly remember Simpson-Spillman codes. And
Yeah, that's fine. I'm not gonna go into details here.
Okay.
So maybe one thing you can think about is, I just want to more basically give a picture here of how these models look like. Right, and how they look like is basically, they look like generalized Ising models, if you would write them down as a physicist. And basically you take some n bits, and then what you do is you choose some random checks or random 4 tuples, for example, and some number of 4 tuples, like some number of constraints. And then these 4 tuples will define your terms in your Hamiltonian. And you just write ZZZ for all the 4 tuples you have chosen and put a -1 in the front, and this is your Hamiltonian. So the ground set of this will realize kind of the code space of some random LDPC code. Where you can think of, you have just chosen some random 4-body checks. So this is the simplest example actually of a good classical code. And if you write kind of this model as a graph, right, by saying, oh, I kind of put my variables on one type of vertex, and then I connect them to kind of an interaction node, like the checks, right? And for example, the ZZZ between these 4 bits, I would connect them up to like a single check node, which corresponds to this particular term. Right, then you get a graph that looks like this. So this is in some sense the interaction graph in physics, or a factor graph, it's sometimes called, or in computer science, it's usually called a Tanner graph in coding theory. So these are all different ways to say the same thing. So these look kind of locally then tree-like actually. So with high probability, you can show that this geometry basically that you're working on locally looks like a tree actually. And then outside, it's kind of randomly connected up. So this is kind of the picture you should have in mind about the simplest version of what I'm talking about. And now to do a quantum code, you take the product. And okay, I'm not going to go into much detail here, but you should think of this really as a Cartesian product. So in the same way that you obtain a torus as the product of two circles, you can take the Cartesian product of 2 of such graphs, and you get something that looks like this. And okay, this is a bit unwieldy, but I guess okay, it's a Cartesian product of 2 tree-like graphs. And maybe the most important thing to realize here is that it's basically made out of squares, right? The local products of edges. And then they fold out into directions, in all directions. They fold out like a book. This is kind of how you should imagine the geometry. And this is something called the high-dimensional expanders. There's at least a few experts, I believe, on this in the room that know much more about high-dimensional expanders than I do. But this is kind of locally how the simplest version of this looks like. And now on this geometry, you could basically define a toric code in the same way you define the toric code on the square lattice. And the Hamiltonian then in the end looks also like a generalized toric code, right? Just like this looks as a generalized Ising model, The quantum version looks like a generalized toric code. You have the negative sum over z checks and x checks, and all of these terms will be mutually commuting. So this is just some stabilizer Hamiltonian. So this is kind of the models we will look at. So they look relatively simple, if you wish, but they live on these kind of relatively abstruse geometries. And just to say it, so this simple construction will not give you asymptotically good code. It will give you a distance that scales as the square root of n. So now you would have to do some more involved construction that involves symmetry and then factoring out the symmetries. This is called the balance product to get actually the asymptotically good codes. But actually locally, they can look more or less the same. If you look around a vertex in its neighborhood, they look actually very similar. So if you just want a cartoon to have in mind, actually in both cases, I think this is a reasonable cartoon to have in mind. All right. Okay, so these are the models. So of course now we want to prove properties about them. And okay, how do you do that? So how does one prove thermal stability? And okay, this is easiest to see actually by returning to the 2D Ising model. And the 2D Ising model, of course, if you are a physicist, you know that it has a phase transition, a symmetry breaking phase transition at a critical temperature Tc. So what this means is that below this temperature, at low temperatures, right, it's a magnet, and there's two stable equilibrium states, which we will call rho up and rho down. And the state here, right, is, you should think of it as a probability distribution over configurations, maybe if you are really not familiar with the physics lingo here. So there are distinct probability distributions which are kind of supported on far away kind of configurations, on configurations that are differ by many bit flips, right? This is the thing to have in mind. And this is kind of what physicists mean, this fact, when they say that the Gibbs state ceases to be unique below Tc. There's actually many ways to formalize this, and I will choose one of them. And that is based on basically ergodic components and dynamics, because in the end, right, we want to talk about self-correction, and this is inherently a dynamical statement, right? We want to couple it to a bath, and we want to see what happens. And okay, so this is formalized by something called the bottleneck theorem. And okay, just to reiterate, right? So really what happens at the phase transition is, for example, if you look at the physical system and you look at the distribution of magnetization, for example, in an Ising model below and above Tc, right? The distribution changes its character, right? This is really what we mean by the phase transition. At high temperatures, the distribution of magnetization, so this is the Hamming weight of the bit strings that it's supported on, is peaked sharply around 0, right? So this is when we say it's a paramagnet. And then below the phase transition, actually what you see is that the distribution becomes bimodal. So it's sharply peaked on two kind of far away distinct subsets of configuration space with some low weight region in between. Right, so here high temperature is in yellow and low temperature is in blue. Right, and this is symmetry breaking because basically the whole the name symmetry breaking comes from this idea that the whole distribution as a whole is still symmetric under inversion of this axis, right? But if you take a single blob, a single mode of this distribution, this is not symmetric. And this is what we call by spontaneous symmetry breaking. And why is this a useful thing to think about? It is a useful thing because actually if I restrict my distribution to kind of one of these blobs here, so if I say I restrict the global distribution to positive magnetization, I take only one half of it, and take this as an initial state for Glauber dynamics, say. So Glauber dynamics is the most common model dynamics to model actually coupling to a bath in physics. So if you take this distribution as an initial state for Glauber dynamics, it will be almost stable. It will actually be almost invariant under this dynamics. So it will not be a steady state. That's the Gibbs state uniquely. But it will have a very long lifetime. And you can quantify this by something called the bottleneck theorem. And what you do for that, the bottleneck theorem in general gives you an idea of, connects kind of dynamics to thermodynamics, if you wish. So it connects kind of Markov chain dynamics to properties of the steady state. And operationally, what you do is you look at configuration space. So this is kind of projected down onto the magnetization axis, but you could think of the whole state space. So say the hypercube for an Ising model. And define a subregion. Z, for example, everything with magnetization greater than whatever, 1%. And on this region, the Gibbs state should have high weight. So we choose something that incorporates this blob. And then the bottleneck theorem bounds kind of the lifetime of the restriction to this set by the so-called bottleneck ratio, which is the weight in this component divided by the weight in its boundary, where the boundary, the notion of boundary, is defined by the dynamics itself. So for example, if you say have single spin flip dynamics, so think of Metropolis algorithm, right? Your bath flips a single spin at a time. You could say, oh, I define some subset of configuration space. I consider all the configurations that are close to, or you can get to from this space omega minus by flipping one spin or two spins. And this defines two set, and you take the ratio of their masses in the Gibbs measure, and this lower bounds the memory time. So this is the bottleneck theorem. And for example, in the Ising model, this lifetime diverges exponentially in linear system size. So you can show actually that if you restrict your Gibbs state to positive magnetization and you initialize this and couple it to a bath, it takes kind of an exponentially long time in linear system size for the system to kind of forget its initial state. But the only thing you use to attain this lower bound is actually a property of this distribution and the fact that it's bimodal. This is really the point I want to get across here.
Is this theorem something that, I mean, is this a general mechanism for proving self-correction, right?
Yeah, this is general. This is of course, yeah. So classically, this is general, and this is of course a very famous theorem. If you are familiar with Markov chains, this is.
But for example, for the 4D Tor code, when they proved the self-correcting, they didn't use this bottleneck theorem, right?
Well, you kind of squint your. I mean, okay. So if you really want to, I guess, prove that if you couple it to a bath and so on. I mean, in some indirect way, you must use it, I think.
Sorry?
Because even if you don't say it, but at some point you say, oh, there's like an energy cost, for example, associated with flipping bits and so on. And then the fact that this implies that there's slow dynamics, that really comes from the bottleneck theorem, even if you maybe don't say it.
So I have a question that actually was asked before in the audience when we had a similar discussion. So how is this different from, let's say, Landau idea of spontaneous symmetry breaking? I mean, how is this? You call it bottleneck dynamics, but it looks very similar to just a Landau theory.
Yeah. No. It's in this case, it's of course the same thing. I mean, at least the temperature that you would see, for example, coincides. Of course, it's really just a different way to mathematically formalize the statement of symmetry breaking. But in this case, you wouldn't get a different answer than if you would ask about Landau.
Can I ask a question? So what is So it's three things that I didn't understand, so it added up. First, what exactly is high weight and low weight? What is the bottleneck here? And what is the memory you're talking about?
What was the last thing?
Memory, I see T mem, I'm assuming it's memory.
Yeah, okay. So, for example, just to do it concretely for the Ising model, right?
What is it?
Sorry?
Sorry, I didn't hear you.
Just to maybe do it explicitly for the Ising model, for example, what you would do there is, so you have a Gibbs state, right? Which is just e to the minus beta e. So this is a distribution over configurations, over spin configurations. And then this distribution, this really assigns weights to subsets of configurations.
Oh, okay. Yes.
Right? And then, for example, in the Gibbs state looks something like this if you project it down on the magnetization axis. So it's bimodal. So what would be a high rate region is I will restrict myself, for example, to states with magnetization between here and here, say. Right? So So this now depends on your temperature and so on, where exactly you would have to change the cutoff, but this would be a high weight region, right? Whereas everything between here and here would be a low weight region. But of course, the point in the end is not so much that you do a cutoff for what you call low and what you call high, but that if you restrict yourself to a high weight region, so if you say you take the distribution that's only kind of one part of it, right? So only like this peak here, right? And you set the distribution to 0 everywhere else.
Benedict, sorry, we're not seeing, when you're pointing something, we are not seeing this.
Control L.
Control L.
Sorry. Yeah, I'm trying to maybe explain this better. So basically, the point of the whole thing is you have, if your distribution is bimodal, if you want to have some dynamics that starts in kind of somewhere here and wants to go somewhere here. So for example, you want to change the sign of the magnetization starting from somewhere over here, right? Then your dynamics necessarily has to traverse kind of some region of configuration space where the Gibbs states has very low weight, where low weight is really relative to whatever weight is outside. Right? So the point is not so much that it's low or high weight, but it's, okay, the time it takes to go from here to here, like very roughly speaking now, you can lower bound by the ratio of weights in here divided by the ratio in here, in this region. Right? So this is this theorem here.
So since someone asked what explicitly these, we call the blues the bottles and the reds the bottlenecks, right? So for instance, if these magnetization peaks, let's say they're at like 0.75, just to pick something, right? That'll depend on temperature. So let's say they're at 0.75 and minus 0.75, then you can choose the bottle as absolute value of magnetization density is, let's say, between like 0.7 and 0.8. And then like the bottleneck, again, this is somewhat arbitrary. It's not going to make a difference in the scaling. And then you can say the bottleneck is magnetization density, absolute value between, I don't know, 0.2 and between 0 and 0.2, right? So that's just one example. And it's like here someone asked about Landau theory. So when you have Landau spontaneous symmetry breaking, that's one mechanism to get bottlenecks, but that's not the only mechanism. And the point is that the formalism is very general. So you can even apply this to active dynamics, and you can talk about when you have long-lived steady states or multiple long-lived steady states. So this applies to any dynamics, and when you have symmetry breaking, that's just one way in which you can get bottlenecks.
And before I was asking about it, because it seems to me like it's very difficult to calculate this, the weight on the bottleneck in various cases.
So again, I think that's where the physics intuition helps. So at least for the Ising model, we can literally adapt Peierl's argument for why there's a free energy barrier in order to calculate the scaling. Like this exact constant C in the equation is not so important, but the fact that it scales like e to the CL, you can really think about as a cost of creating a domain wall and sweeping it across the system, the free energy cost. So this is just related to, it's literally a free energy barrier because, the Gibbs state is e to the minus f, right? Beta f. So this is just a free energy barrier. And when we have a physical perspective, then kind of you can use physics to figure out the scaling of this.
So you said before that you can understand also the four-dimensional theory code through this kind of variables or these peaks. So what is it that you really gain now from this kind of LDPC or quantum LDPC based on these expander codes that you somehow couldn't understand before?
Well, okay, so this I'll talk about a bit. I mean, in the quantum LDPC code, for example, we can explicitly show kind of that there are distinct high weight regions of configuration space, which are kind of separated by low weight regions. And that tells you that there is distinct states which are dynamically stable under some dynamics, which emulates an LDPC code coupled to a bath.
So you get more stability than what you had before.
Sorry?
Somehow you can distinguish more between the different peaks. Somehow it's like more stable than you had before.
Well, what do you mean by before?
Say from the four-dimensional Tori code.
I mean, the four-dimensional toric code is just a different code, right? Like it's, if you want to understand the properties of good LDPC codes, it's very different setting from the 4D toric code. Like K is different, D is different, it lives on an expander graph. So just because the 4D toric code had bottlenecks and free energy barriers, by the way, and that's something that's not yet even been proven. We're working on that because this quantum bottleneck theorem didn't exist. So this kind of picture for the 4D toric code in terms of bottlenecks didn't exist. But even saying that works out, which it does, the mechanism for why the qLDPC code has a free energy barrier is completely different from the 4D toric code, right?
Benedict, I want to explain Tali's question from a different perspective. We were discussing earlier today the following thing, that the 4D Tor code is self-correcting, but it's almost LTC, but it's not, right? Because the ratio between the size of the error and the energy is not constant, but it's constant. It's 1 over, I mean, it's the area compared to the volume, right?
Yes.
Yeah.
Whereas these codes are LTCs, or at least they have some properties. They're closer to LTCs. They have classical LTCness. Do you gain anything in the stability because you move to higher dimensions, or it's just a new construction that is in higher dimensions?
Well, it depends which codes you're looking at. I mean, if you look at the asymptotically good code, actually, right, then of course this is actually e to the cn instead of e to the cl, which would be square root n here, right? So this is just a result, but this is also you have to show, of course, right? But this is what you find. So it's more stable in the sense that the lifetime has a different scaling. It's exponentially in n rather than square root n.
So the distance gets into the time of the memory.
Yeah, it enters the time scale of the memory. For the hypergraph product codes, for example, right, which are not asymptotically good, you actually have a square root n up here, for example. So that would be similar to the 4D toric code, say. Or not, 4D toric code, of course, has like a cube root or something. But it would be similar to the 2D Ising model in that sense. But of course, then it has finite rate, for example, like constant rate, which is at a very different setting.
Okay.
And again, so in the Ising model.
Another follow-up question?
Yeah?
One more question. You mentioned here that you consider multiple ergodic components, but what is your reason? So, and how to see that you have different ergodic components here? You mentioned Markov chain before. Does it mean that it splits into several non-interactive components or something like that? So,
yeah. So the question is, for example, if you look at this, so what I'm really doing here, right, is I separate the configuration space into different regions, basically into high weight and low weight. And now basically, if you can choose distinct kind of regions which are surrounded by a bottleneck, right? So there's 2 blue and they are both surrounded independently by a red low weight region. They both have large lifetimes, right? But they are both distinct from the global steady state.
So you mean that they can interact, but in some sense very, very large time, so you can consider...
Exactly. The global steady state is unique, but these are 2 very different, long-lived kind of initial states. And this is what I would call an ergodic component.
Okay, I see.
And then, of course, you might want to choose like a cutoff here, that whether it has to be exponentially long-lived or polynomially long. But in this case, for example, there's 2 states which are distinct, and they're both exponentially long-lived under Markov chain dynamics.
One more question. Is there a difference between lifetime if you have linear distance finite rate versus linear distance and zero rate?
Well, that would be basically the question of how many distinct states are there that are long-lived, right? So this would define some effective rate.
Does it affect the scaling or no?
No, I mean, for the good qLDPC codes, you have like exponentially many in system size components, and they are all exponentially long in system size lived. So you can, so I think these are more or less separate properties, how long the components are lived and how many there are. But they're both interesting, of course. All right. So maybe this is a good point to say, okay, so in this case, for example, I can define two states, right, which are long-lived, and they are different. But they are related by kind of a global symmetry of the system. So if I flip all spins, I go from this omega plus to this omega minus. Right? And this is, I think, what sets kind of these kind of systems apart from something like spin glasses. Because in general, right, I can think of a distribution which has kind of a lot of kind of these lobes or peaks where you have high weight and which are surrounded by low weight regions, right? So these are all kind of individually stable states under a Markov chain, but they're actually not related by some symmetry, and they don't look the same. There's no reason why they have to. And this is kind of what we mean actually operationally in our case by a spin glass, and this is the thing that we prove, that this is that even for these kind of random codes, for example, it looks much more like this than like the Ising model. And just to quantify this a bit, for example, one way to say it is, well, if you do some decomposition like this, what you can do is actually you can write the global state as a sum over these components, because these are by definition disjoint regions. And now if you normalize kind of the restriction individually, you get some kind of local Gibbs state, if you wish, and you get an associated weight, Wi. And these Wi's, if you've done the composition correctly, they almost sum up to 1, up to some error term. And if I ignore the error term for a second, you can treat this all rigorously, but okay, let me for the discussion here, maybe ignore the error term and say the Wi's define a distribution. And then you can actually characterize kind of the system or your Gibbs state, if you wish, by properties of this weight distribution over components. And there is now a bunch of things that you can compute. The most natural quantities maybe are entropies. And there's two entropies that we explicitly bound in our paper. And this is the Shannon entropy of this Wi. And this is also called the configurational entropy, if you've heard this. And this is really just, the Shannon entropy of the Wi distribution. So this just tells you how many components are there, roughly speaking, or how many components of similar weight are there, right? So this is what the Shannon entropy is. And then the other thing we look at is something called the min entropy, which is just the negative logarithm of, but it's really just the size of the largest component. Right? So how big is the largest kind of blob that is invariant under the dynamics? And then operationally, what we call a glass, we want two properties for a glass, or what we call spin glass order in our case, or the property maybe I should say that we prove really is first there's two things. There's shattering. So maybe some of you have heard. This is kind of a standard term in the spin glass literature. And this just means that each of these kind of Gibbs state component has exponentially small weight. And what this means operationally is that if you initialize your system in any initial state, it will only explore for a very long time kind of some very small fraction of the configuration space. Right? This is really what shattering means. And technically, how you would show it is that you show that the min entropy is kind of greater, the density, right? So here's an NS. The density is greater than 0. So there's a finite min entropy density in the system. And another thing then that we want for spin glasses is that actually almost all components do not contain ground states. So what this means is that, for example, what this operationally implies is that if you do, for example, cooling dynamics in your system, if you think of cooling the system down as a physicist, or doing simulated annealing of some corresponding constraint satisfaction problems, this actually gets stuck in local minima. Because if you think about cooling slowly, you will be in equilibrium at some temperature, right? And now you will get stuck in one of these components, more or less a random one. But then almost surely this one actually doesn't contain a ground state or a solution to your problem, right? But you are stuck because this component is long-lived. And so now if you cool further, you will not be able to reach the ground state because you will not be able to escape this component that you're stuck in. And this you can connect again to an entropy, but in this case, it will be the Shannon entropy of your distribution, of this weight distribution. And we say that the system is incongruent if the Shannon entropy at finite temperature is larger than at zero temperature. So at zero temperature, this is just the code rate. I think somebody asked this before. So the zero energy configuration entropy just becomes the code rate, right? Because the only things that are relevant are the ground states. And these are your code words. But at finite temperature, there can be more things emerging, right? So these will be these local minima that I kind of sketched in the beginning and that I will have in the next slide again.
So this also connects with the questions that are being asked on symmetry breaking, because like when we talk about symmetry breaking, then it's always ground states related by symmetry. But here, most of these components do not contain ground states, so most are not related by the action of some symmetry.
Yeah.
Yeah, so this is the glass, right? So can you remind us, please, do spin classes exist in finite dimension? Like on lattices or?
That is a big question. I think if you go to Wikipedia and look at the list of unsolved problems of physics, this is number 1 or 2. Well, we don't know. And the big question actually is, are there many states or are there not many states, right? This is the big debate that people have been agonizing over for 40 years now.
But so suppose someone finds a spin class in constant dimension, this this would give, first of all, it is a quantum memory, right?
So in our case, it is. I mean, this doesn't imply quantum memory because I haven't specified yet what properties these kind of components have, right? So far, everything that I talked about could be classical, right?
So all this is quantifying, and this will be in the next slide. Benedict will clarify this, I think. Like all this is quantifying is what it means. Like people often use the word spin glasses have rugged free energy landscapes or complex free energy landscapes. So, so you picture some like rugged landscape with lots of global and local minima. So this is just quantifying what do we mean by a complex free energy landscape in terms of these decompositions, right? So it's saying that one, you should have exponentially many stable minima, and that most of those should be local minima rather than global minima. Right, so that this is just putting words on that. And once you have that kind of feature, you can use it for a classical memory always. But now the question is, okay, if you want to use it for a quantum memory, then we have to do some extra stuff in terms of what the nature of the minima should be.
Maybe you said it, but I did not understand. Can you say when the glass appear in what temperature in this structure that are related to this quantum stuff?
Or what do you want, a number or so we cannot compute. We don't know where to compute the number.
Sorry, Benedict, we didn't hear you.
So do you want a number or
just roughly if it's like close to 0 or it's like far from 0?
It's some order 1 number.
It's some finite temperature, yeah.
I don't actually know. It was not insanely low actually. Maybe 0.2 or something like this, 0.5. I don't know. I don't remember actually. It also depends, of course, on the specific model that you choose.
And I mean, I think one other thing to emphasize is that there's a sharp glass transition temperature, which is purely dynamical, which is when all these components become stable. And that has nothing to do with thermodynamics. So you can look at some partition function, and the partition function, and this is true of glass problems in general, that the partition function can look perfectly analytic at every temperature, but nevertheless, you can have a sharp dynamical transition temperature. And that's usually at some order 1 value in terms of some scales in the problem.
Yeah, that's a very good point. And this is also, of course, connects to this idea of, okay, why do you have to do this kind of stuff instead of just doing Landau theory or some more traditional things? Is because, for example, you wouldn't see it in the partition function.
Exactly.
these transitions.
So like unlike the 4D toric code, there is something sharp happening in the partition function. So you can do conventional thermodynamics and pick this up. But if you try to do this for these glass problem or for these LDPC codes, you would think that there is nothing going on. But actually that's where the glass picture is useful. Yeah.
Yeah.
So you say that somehow here you have a new way to get the glass, which is what you said, while for the 4D toric code you use somehow a different method, or somehow it's obvious for a different reason.
Well, the 4D toric code, for example, all the kind of components that are stable look the same.
Okay.
That is the one clear distinction to the setting here in the LDPC codes.
Okay, so we are, I see that people are starting to get a little bit, we're at the end of the day, so maybe we'll take a few more minutes and...
It's very good. Actually, I think my next slide is a good place to stop.
Oh, great. So that
because my next slide now has why is it topological? Because now we have like, okay, this is what we mean by a spin glass, right? And okay, there's all kinds of things, how you prove this and so on. This gets very complicated, but okay, this is kind of the properties that we want to prove. Right? So we think of a Gibbs state as a distribution and we prove these properties of the distribution in essence. And again, to reiterate, this will be very different from, say, the situation in the 4D toric code, where, for example, all the stable components, as soon as they get stable, they include, for example, ground states, basically, or they're continuously connected to the ground states of the code.
Mm-hmm.
So you can cool the 4D toric code, for example, into its ground state easily. Okay, so what is the addition? So why do we call it topological? So everything I told you so far basically was a definition of spin glass that would apply to classical and quantum glasses. So as Vedika said, right, this kind of is supposed to quantify these cartoons of this free energy landscape. And okay, so then let me say what is the finally kind of all the properties summarized of these LDPC codes that we prove. Okay, just as the cartoon, the energy landscape of these models looks something like this. So of course, it's an LDPC code, so actually it has logical operators which commute with all the checks. So there is actually symmetry in the system. The point is that the symmetries are not all there is to it, right? So if you look at now the landscape, it will be kind of consist of multiple copies of the same thing, which are kind of correspond to logical sectors of your configuration space. And there's 2 to the k of them, k being the number of logical operators. And in each of these sectors, you have a single ground state, a single code word, naturally. But then you also have a lot of actually local minima or other stable states within each sector. Right? And that, for example, would be very different. This would look very different for the 4D toric code, where we would have like kind of only one kind of local minima per logical sector, just to reiterate. And the interesting thing is now that you can build quantum codes from both kind of global and local minima. So in addition to this classical complexity, shattering, and congruence, which we are able to show, we can also show that kind of the states that live in these minima, right? So for example, the things that I've kind of colored in light and dark blue are long-range entangled, right? So these host some state. You take rho e to the minus beta h, and then you restrict it to the subspace that is defined by the local minima. This gives you density matrix, and you can ask, can you approximate this density matrix by a mixture of low complexity quantum states? And the answer is no. So this is the first thing where you would call it maybe topological, right? So it's long-range entangled, really. And this you can show. And then the other thing is that it's a quantum memory, it's self-correcting, but there's actually also emergent quantum memories. In the sense that in this picture up there, the states in dark blue, these are the ground states, and they would be conventionally what you would use as a quantum memory in this setting, right? If you define the code, and this is where people say if they write down a good qLDPC code and they write down the stabilizers, this is the states that they would intend to use. But it turns out actually you can be self-correcting not only with respect to this code, but also with respect to some of these local minima. So if you now take kind of this selection of light blue minima that I indicated, this is just as well a self-correcting quantum memory as the other thing. Under the same dynamics. So you could even use them simultaneously under the same passive dynamics. And this feature you wouldn't have in like a more conventional self-correcting quantum memory. And this is really why we call it topological glass. Right? So it's topological and it's a glass. And both of these things are true. And yeah, this in the end justifies the name. And maybe this is a good place to stop, actually. And then I would have now talked about how do you prove this and so on, but I think this is now a good place to stop. There were many questions. I don't want to keep everyone awake even longer.
Thank you very much. Maybe we'll have one or two questions just from the audience.
So perhaps you mentioned that, but can you do that for any good quantum LDPC code, or it need to obey some additional conditions?
Yeah, okay, so now the question is whether I have my physics or my math hat on, I guess. So as a physicist, I would say all the constructions I know and that I've tried, they work. If you do numerics, for example, and you try to see whether these consistents are... So our proof actually works for hypergraph product codes and for good codes with sublinear number of redundancies. So there is a condition on the redundancies that we are using to show the incongruence. So the self-correction is a property of every good code, for example. And so is the shattering. The incongruence, so what makes it a glass, for that we technically in the proof use a lack of redundancies. So meta checks, if I don't know what your background is and how familiar you are with these words. So the checks should all be mostly linearly independent, basically. And otherwise our proof technique kind of just doesn't work. And this might of course be a technical issue. And actually if you try, for example, and you construct these codes, they tend to have few meta checks, right? They're not LTCs in another way. Is another way to say it. Yeah, this is a condition that we need.
And then maybe another question, maybe you also mentioned a bit that a little bit. So there is the people who gave recently constructions of NLTCs, no low energy trivial NLTS, sorry, no low energy trivial state. So
yeah.
Is what you're showing equivalent to that, related?
For the good codes, yeah, they are somewhat equivalent. For the good codes, actually, so we have actually used a different proof because our proof also applies to hypergraph product codes, but it doesn't show NLTS in that case. So what we can show is that if you look at these local minima, within each minima, you actually have kind of some NLTS-like property. So the way we prove this long-range entanglement is by proving circle complexity bounds for any state actually in the minima, which is stronger than what you would need for just topological order. And now if you have a good code, kind of there's only local minima at low energy, and then you are done and it would imply NLTS, although it's a different proof. And for the hypergraph product codes, there's some other stuff somewhere. So there could be like rare states that are not entangled. And so this we can't exclude fully in this case. And so it's closely related, I would say, but it's not exactly the same. It's only the same in the case where you have a asymptotically good code.
Okay, we have a stamina for one last question.
So I guess quantum topological order should be stable against any kind of perturbation. Is it also true for the classical case? Say if an perturbation would break all the symmetries in the model.
Yeah, very good question. I guess Vedika has a beautiful paper that I'm not on about the stability of ground states of stabilizer models, even in these non-Euclidean settings. So this was already non-trivial effort. So that's true. So the ground states are stable. The degeneracy and I guess the gap is the technical statement. Maybe Vedika can just answer the question instead of me.
Right. No, so the ground state properties are stable, but then in our bottleneck paper, we also showed that for the good codes in particular, which have these linear barriers, that the bottlenecks are also stable. And again, one way to think about it is that when you have a linear, linear meaning extensive and n free energy barrier, any term you add to the Hamiltonian can only change the energy by at most some extensive amount. So again, it can also only change the free energy by at most, like you can always make the terms small enough or the temperature small enough that your bottlenecks remain stable. So the extensive scaling, which is a unique feature of expander graphs, really helps there. So there we were also able to prove the stability of bottlenecks.
Yeah.
So in that case, the glass would be stable. Yeah.
Yeah. Yeah. So it's the same about linear energy barriers, and everything is always stable fully. And then the hypergraph product code, there's a proof for the ground state properties. I guess this is one way to summarize it.
Yeah. And we strongly believe it should be stable also for hypergraph products, but that we've not proved yet. Yeah.
Yeah.
Okay. So thank you very much, Benedict. Thanks, Vedika. Good morning.
Thank you for staying.
Good time to us. Thanks a lot for joining.
Yeah. Thank you,
Thank
Dorit.
you.
Hi.
Sorry?
Oh, hello. Hi. How are you?
So let me see. Yeah, can I hear you?
Yes. Hi.
Yes, great. So my question is about the dynamics. So my understanding about classical systems is that the spin glasses are related to closed system, that there is just no buff. And now if you add a buff, I mean, wouldn't it make it thermalize and so become ergodic?
No.
No, because you have a free energy barrier, right? So again, think of an Ising model. You have a 2D Ising model, it's a closed system. But now when you're doing Glauber dynamics, in principle, you're coupling it to a bath. But because the system had some large free energy barrier.
No, but I mean, Glauber dynamics, this is the question. I mean, how do you do Glauber dynamics? I mean, you need the coupling to a buff, and then the buff will have, I don't know, some fluctuations in it. And
Right. But I think the whole point of Glauber dynamics is that it prepares the global steady state, right, by coupling to a bath. And what these bottleneck theorems prove is that when your global steady state, which is the Gibbs state, the global Gibbs state, e to the minus beta h, when it has these distinct components, then if you start in one of the components and you do Glauber dynamics, you are stuck there for a very long period of time. So it's all consistent in that if your open system dynamics is designed to prepare the global Gibbs state, has the global Gibbs state as its late time steady state, then these results will hold. But if you just couple to some crazy bath, break detail balance, do some like violent things in your system that don't prepare the global Gibbs state, then we can't say anything, basically.
okay, so some weak coupling to a buff.
Yeah.
That's certainly true.
Mm-hmm.
Okay, thanks a lot.
Okay, thank you. Yeah.
Thank you. All right. Yeah, thanks for coming.
All right. Bye.
I have a date with Sorry?
Thanks for giving the talk. Yeah.
Yeah, thank you. Having a date with Tibor to discuss our the response on Thursday morning. So
okay, great. All right.
Let's see where we get.
Yeah. Okay.
All right. See you.
Bye.